Hello, welcome everyone. So I'm going to continue with quantum numbers now, and it's basically an address for where the electron lives. And then I'm going to talk about how you write that address. We call that electron configuration. Okay, so the first quantum number we're going to talk about is the principal quantum number. This is given the letter N here. And this basically tells you the size and the shell that it's in. So you can only have integers starting with 1, 2, 3, all the way out to infinity. So notice that we do start with n equals 1. That's the ground state. So n equals 1 is the lowest energy 1. And as n increases, we get further from the nucleus and size increases. The next quantum number is the L quantum number. It stands for angular momentum. And the possible numbers can be n minus 1 all the way down to 0. So for example, if n equals 1, if I'm in the ground state, I can only have an L equals 0. That's because n equals 1 is a ground state, it's small, I can only fit in an s orbital. What I'm going to tell you here is that L is going to have certain numbers, and they refer to the different orbital shapes. L equals 0 is an s. If I get into n equals 2, there's more space, so I can have L equals 0 or L equals 1. So notice, be very careful. A lot of people, they think L is only n minus 1. So they think L is only 1. But it could be 1 all the way down to 0 and all integers in between. So in n equals 2, if you remember from the last video, you can have an s or a p orbital, a 2s or 2p, referring to L equals 0 for the s and L equals 1 for the p. So this is something you just have to memorize. L equals 0 is s, 1 is p, 2 is d, and 3 is f. Always. You can always count on that. The shapes are the ones that I've already shown you. Spherical for s, the infinity, clovers, and f's. Okay. The third quantum number is the magnetic quantum number. We give this an m sub L notation because it is dependent on L. So just remember, this is related to L, which dictates the shape. So the possible numbers is minus L to 0 to plus L. Okay, let me tell you what this is. This actually gives the 3D orientation or direction in space. So if L equals 1, m sub L could be minus 1, 0, or plus 1. Hopefully this makes sense. If L is 1, you have a P. If L is 0, first of all, you have an S, and there is no other direction. M sub L can only be 0. But if you have an L equals 1, that is the same as a P, and you have 3 different directions. Remember, Px, Py, Pz. That's why we give m sub L's. M sub L is basically to label, do you have Px, Y, or Z? I don't need you to know that m sub L, m sub L equals minus 1 is a specific direction in terms of, oh, that's definitely Px or that's definitely Pz. I just need you to know it's one of the directions. And we put it in the order minus 1, 0, plus 1. Okay, if you have an L equals 2, you know that's a D. So m sub L can be minus 2 all the way to 0 and to plus 2. So for the D's, we have minus 2, minus 1, 0, plus 1, plus 2. So we have 5 different ones for the 5 different orbitals. So notice the m sub L is just to give basically a label to which d orbital you're talking about. The other thing I want to show you on the slide is that each orbital, basically each line here, each orbital in S, a Px or a Py or a Pz or one of these Ds, they can hold a maximum of 2 electrons. So they can hold 0, 1, or 2 electrons. And so the one thing I need you to understand and just note is that for an S orbital, you only have one line, one possible orientation, so one type of orbital. So an s orbital has a max of 2 electrons. When you go down to the p orbitals, you have these 3 different directions. Each of these different orbitals, p, x, y, and z, can hold 2 electrons each for a maximum of 6. And then since there are 5 Ds, and you can have 2 in each, you have a max of 10. If we were talking about the Fs, you would have 7 different orbitals that can hold 2 each, so Fs can have a max of 14. This is helpful when we start filling up orbitals. All the S, or the S can have a max of 6. All of the 3 Ps can hold, sorry, just to make sure I said that correctly, an S can hold a max of 2. All the 3 Ps can hold a max of 6. All the 5 Ds can hold a max of 10. The last quantum number that I want to show you, and this should be number 4, is the spin quantum number. So electrons can have different spins. One way you could think about that is that it's like on an axis, a sphere on an axis spinning in one direction or the other. But we call these directions up or down. And we give an up spin a +1/2 number, and we give a down spin a -1/2. We show electrons as an arrow. So this arrow here is the single electron in the hydrogen atom. I put an up arrow because that is by default, the first one you put is spin up. So the m sub s is +1/2. Look at what I did here. I have hydrogen, it has a Z of 1. Don't forget, Z is the number of electrons and protons and neutrons in a normal atom, neutral. And so Z is atomic number. So it's number 1 here for hydrogen, which means it has 1 electron. It also has 1 proton. So that 1 electron is going to go in the lowest energy orbital that's closest to the nucleus. It's the 1s orbital. I label this as 1s. I put a line. You can use boxes. And I put 1 single electron with a spin up. We know that that electron belongs to hydrogen, and this is where it's going to be located. Sometimes we want to give an address. So a way to do that is to give the quantum number set. That big 1 there refers to its level, n equals 1. The L is 0 because I'm talking about an s orbital, and by definition, L equals 0 is an s. And then since s only has 1 orientation, m sub L is also 0, and m sub s is +1/2. So if I wanted to give a full quantum number set, n equals 1, L equals 0, m sub L is 0, m sub s is +1/2. Okay, I want to talk about how many electrons can be in each shell or level. These are used interchangeably. First of all, let's look at just kind of a basic stripped down version of the model of the atom. We have the nucleus in the center, n equals 1 here. N equals 1 can only have a 1s electron. Sorry, a 1s orbital to hold a max of 2 electrons. So for n equals 1, you can have a 1s, max of 2. And so we show 2 electrons here. First shell can have a max of 2. When you get into this green n equals 2 level, if n equals 2, you can have an L of 1 or 0. So you could have 2s or 2p. So the 2s has 1 orbital. The 2p has 3 of them, the p, x, y, and z. So I have a total of 4 orbitals, which can hold 2 each. So 4 times 2 is 8. So in this green, we call it level or shell, I can have a max of 8 electrons. If we do n equals 3, you could have a 3s, 3p, 3d, so to a total of 1 plus 3 plus 5 orbitals. That's 9 times 2 electrons each. I could have a max of 18 electrons. You could keep going for the Fs. I just wanted to show you how you can figure out how many electrons are in each shell. Now let's get into actually filling up where the electrons are for another atom, so not just a hydrogen atom. There are a couple things you need to know. The first is this Aufbau principle that says fill the lowest energy orbitals first. The reason is the universe tends towards lower energy. electrons closer to the positively charged nucleus are lower in energy. So we'll use this order. I'm going to also show you how to do this by not memorizing this order, but just by looking at the periodic table. The Pauli exclusion principle tells us that an orbital can hold only 2 electrons, each of opposite spin. So one spin up, one spin down. Also, if you have orbitals that have equal energy, meaning the p, x, y, and z are all p's, they have equal energy, but they are 3 different orbitals, you basically want to put an electron in each of those first before doubling up and filling 2 in each orbital. This is called Hund's rule, and it minimizes repulsion. So let's look at an example with oxygen. Z, or the atomic number, equals 8. So it has 8 protons, but more importantly for us right now is it has 8 electrons. So I'm going to fill those up. I'm going to fill the 1s first, and I could fill first an electron spin up, then electron spin down. Okay, now that's full. So now I need to move to the next one. I go to the 2s, an electron up and down. Now that's full. So I go to the next, which is the 2p. I put an electron up, but now based on Hund's rule, I space them out. So the next go spin up in different ones is to minimize repulsion. It's almost like getting on a bus. If there was one person on a bus, you don't go sit like right next to them unless you know them, but you spread out first before doubling up. I said Z is 8. So there are 8 electrons. I already used 1, 2, 3, 4, 5, 6, 7. So the 8th electron then doubles up here as a spin down. Okay, so that's what we call an orbital diagram. Sometimes we don't want to write the orbital diagram, but we actually just want like a really brief notation to show where the electrons are. We call that electron configuration. And basically we use superscripts to show the number of electrons in each orbital. So here I have 2 electrons in a 1s, so I write 1s2. Here I also have 2 electrons, but now in a 2s, so I write 2s2. And here I have 4 electrons in a 2p, so I write 2p4. That is the full electron configuration for oxygen. Later, I'll also show you some shorthand notation. But I also want to show you how to do this using the periodic table. So basically, if you can just create these sort of blocks of elements, here we have an S block for the first 2 columns. The last 6 columns, we call this the P block. And the center, transition metals, are the D block. Down here, the actinides and lanthanides, they're the F block. So you can actually do this electron configuration just by looking at the periodic table. So basically oxygen is right here. The way this works is you go left to right, then you go down. So you fill up a 1s orbital first. Then you fill up a 2s, which is what we did. Then you go next to the 2p region. And you count 1, 2, 3, 4 to get to oxygen. And so that's why the electron configuration is 1s2, 2s2, 2p4. Notice that there are 6 spaces here for the 6 available electrons that can be in a p orbital. If you were looking at titanium, which is down here, you would have done everything else the same. You would have actually done 2p6, 3s2, 3p6, and then 4s2. And then notice the D block starts at 3d. So then you do 3d, but only count 1, 2, because titanium's right here. So you'd end with 3d2. Sometimes we identify inner and outer electrons. The inner electrons are the core electrons that aren't very reactive. The outer ones are more interesting. Sometimes we also call those valence electrons. Those are the ones involved in bonding and are more reactive. So we've already gone through the electron configuration of oxygen. It's this, shown here. What are the inner electrons? Basically, the inner electrons are the core electrons that are basically everything up to the previous noble gas. So if you look, the previous noble gas is helium, 1s2. So for oxygen, the inner electrons are helium. Later on, when you get to a little bit more involved atoms, Also, fully filled Ds or Fs are not reactive, so those end up being inner core electrons as well. What are oxygen's outer electrons? These are the highest energy or outermost ones. So for oxygen, they're the 2s2 and 2p4 electrons. So oxygen has a total of 6 outer electrons and 2 inner electrons. Notice that even though the 2s is filled, it's still in the outermost shell of n equals 2. So that's why it's used, it's available for bonding. And if you notice, if we add these up, 2 and 4, it's 6. Oxygen does have 6 outer electrons that are its valence electrons available for bonding. You may remember that from electron dot structure. Okay, so far, maybe you've taken it on faith why we have these different energy levels. I want to explain to you why that is. So first of all, when we start looking at atoms other than hydrogen, there are a couple different factors that are involved that can change the energy level of the orbital. One way to think about it is changing the energy level of that electron, how much of that positive charge it feels from the nucleus. So if it can feel the full positive charge of the nucleus, it feels the full Z. Like hydrogen, that one electron feels the full 1+ positive charge from the one proton. However, when there are other electrons like in the way or there's repulsion, there are more inner electrons, it cannot feel the full positive charge. So we call that something less, and we call that effective nuclear charge. And we give it a Z, EFF. And basically it's saying like it's something less than the full Z. Okay, so there I would look at your textbook and look at some pictures on basically just seeing if there's some electrons blocking or in the way, some inner electrons, then it's basically like shielding and it can't feel that full positive charge. The other factor I mentioned is the shape. I mentioned that S can penetrate more closer to the nucleus. It feels more attraction to the nucleus than P's, D's, or F's. So that means those further out, if there's electron density further out from the nucleus, it doesn't feel that positive charge. So I write that a little bit more. S orbitals feel more positive charge, so they're lower in energy. Again, if that's confusing to you, just think of lower in energy just means more stable, feels more of a attraction, more of a solid connection with that positively charged nucleus. So an electron, for example, in a 2s has less potential energy than one in a 2p. So what that means is an electron in a 2p orbital, it's further from the nucleus, so the 2p has higher potential energy. It's again like an electron being stretched out by a rubber band. So it's further out. So if you let it go, it'll snap back and it'll release more energy. Okay, let's do a little bit more with electron configuration. Sometimes when you're looking at elements way down here, we're going to look at zinc and lead. It's just really tedious to write out the full electron configuration. So we use a shorthand. We basically use the previous noble gas, its symbol in brackets. So if I do zinc, which is Z equals 30, it's right here. Let's do the full electron configuration. Starting from the top, we fill up a 1s, and then a 2s, and then 2p. Notice the p's start at 2. So notice the s's. If you number from 1 all the way down to 7, it starts at 1 and goes sequentially. The p's, though, don't start until n equals 2. So you start here at 2. This is the same level as the s, so that's easy to remember. So after 2s, you fill up the 2p. So far we have 1s2, 2s2, 2p6. And then we go to the next level, 3s, so 3s2, and then 3p6. And then we go to the next level. This is 4s. This 3d is just written out here because it's too crowded, but the d's don't start till you get to n equals 3. So this d block starts with 3d. So we'll fill up the 4s and then 3d. And then we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d10. So if you haven't picked up on this, as you go across the periodic table, you add a proton, neutron, and an electron. So that's why each time I go, I'm adding one more electron into that space. Until you fill it up, then you go to the next level. But at zinc, I would have stopped at 3d10. If I didn't want to write all that, I could have just gone back to the previous noble gas, which is here, which is argon, and just bracketed argon. So what that means is when you bracket argon, you're saying, oh, I have the full electron configuration up to argon, and then continue 4s2, 3d10, done. Let's do lead that way. Lead is here, Z equals 82. Let's go to the previous noble gas, which is here, xenon. So I'm going to bracket xenon. Then after xenon, I go to the next level, which is 6s. I'm going to fill up 6s, and then I'm going to go here. I'm going to go 5D, because D start at 3. So 3, 4, 5D, and I'm going to fill up the Ds. But look at this. Something slips in here. It's the 4F. This is a tricky one. I'm not going to try to trick you on these, but I just want to show you how this works. 4F slips in here. That's the inner transition metals. So you would actually fill up the 5D10, then 4F14. And once that's done, you're here. And then you get into the 6P. So I wrote it here, but again, if you don't have it written, 2P, 3P, 4P, 5P, 6P, and I count 1, 2, 2 to get to lead, so it's 6P2. Okay. There are 2 exceptions I need to talk to you about, and that's in the D4 and D9. So D4 is 1, 2, 3, 4, this chromium, molybdenum, tungsten column, and D9 is here, copper, silver, gold. Just to let you know, these guys are just 1 electron away from getting to a half-filled D, and these guys, D9, are just 1 electron away from getting to a fully filled D. If you can make a fully filled or half-filled D orbital, this is energetically favorable. Some of the reasons involved just basically minimizing repulsion, and also a fully filled D is more stable. So chromium, for example, which you would have expected to be argon 4s2 3d4, is not that. When you do experiments, you actually find that an S electron jumped to a D. So it's actually 4s1 3d5. So that happens with chromium's column, the D4 column, and copper's column, the D9. Copper is not 4s2 3d9, it's actually 4s1 3d10, because an S electron jumped to fill the D. So do not do this with other orbitals. Do not do this sort of jumping with p orbitals. Sometimes you see it with F's, but it's not predictable, so I don't expect you to do that. Only do this with d orbitals, the D4s and D9s. Okay, let's end with a little bit of practice. A couple questions here. Answer these, pause this, and then I'll go over it. So the first one is, what is the maximum number of electrons in the n equals 2 level? And then how about if you had n equals 4 and L equals 1, this additional constraint? The next one is, give me the electron configuration and partial orbital diagram for selenium. And then tell me the number of inner and outer electrons. Okay. So the answer to this, the first one is the maximum number of electrons in an n equals 2 level. N equals 2 can only fit a 2s and 2p. So you have a total of an s orbital and the 3 different p's. So 4 different orbitals that can hold 2 electrons each. 4 times 2 is 8. The second one that has a little bit more of a constraint, you have n equals 4. So you could have 4s, p, d, and f. But I say L equals 1. I told you to memorize L equals 1 is a p orbital. So that means you're limited to 4 p orbitals, the p, x, y, and z. So 3 orbitals, 2 each, a max of 6 electrons. So that's only because I gave you this additional constraint. Okay, write the electron configuration for selenium. It's argon 4s2, 3d10, And then in the P block, in the 4p area, you go 4 across to reach selenium. Notice that selenium's in the same column as oxygen. So hopefully you see that all of those in the same column have the same ending electron configuration in terms of the number of outer electrons. It may be a different n level, but oxygen had a P4, sulfur will have a P4, and selenium has a P4. That's why elements in the same column have similar reactivity. They have the same number of outer or valence electrons. So let me ask you now, how many outer electrons? The core inner electrons are argon, but also this is special because this D is fully filled, it's also an inner electron, just because it's not really reactive. Outer or valence ones are the ones that are going to be more reactive in this outer 4s2, 4p4. So the outer ones are a total of 6 here. And you can count the number of inner ones 2 ways. You could just take the total electrons from the Z atomic number and subtract the outer. So that would have been 34 minus 6, 28. Or you could have literally counted up the total for argon, 18, plus the 10 in the D, and that's 28. Okay, I'm going to end here, and we will continue with more videos at another time.